Thank you all for attending the webinar for today. We apologize for that slight delay on getting all things ready, but we are now ready to commence. So before we get started, I want to review a few items so you can actively participate in today's web event. Here we are looking at an example of a GoToWebinar attendee interface, which is made up of two parts. The viewer window is where attendees see the presenter screen, and also the control panel, where attendees can interact with organizers. You should see something that looks like this on your own computer desktop in the upper right-hand corner. Clicking the arrows on the Grab tab opens and closes the control panel. The audio pane provides audio information. There are two options. To join audio through your computer, select Use Mic and Speakers. Click Audio Setup to select your computer speaker or headset device. You can also join audio through your telephone. Select Use Telephone option, dial the number listed and enter both the access code and audio PIN when prompted. During the presentation, you have the ability to send questions to our webinar staff through the questions pane. Simply type in your question and click Send. There is also the option of asking questions directly to the presenter. To do this, raise your hand and we will unmute your microphone. This option is located on the Grab tab. At the end of the presentation, we will do a question and answer session to answer as many questions as we have time for. If you prefer to keep your control panel open during the presentation, click View in the top menu and uncheck Auto Hide the control panel. Our presenter for today is Alistair Webb. Mr. Alistair Webb is Geodynamics Commercial Manager. Alistair manages the rapidly increasing commercial aspects of geodynamics progress, including external relations, future contractual arrangements, transmission and other opportunities with new prospects. He holds a Master of Applied Finance, a Bachelor of Science, is a Chartered Accountant, and has 15 years experience in electricity generation and accounting advisory roles. He was formerly the Manager of Energy Derivatives at Eraring Energy in New South Wales. I will now pass you over to Alistair to commence the webinar.
Hi. Now hopefully you'll all be able to see my screen here, and I'll start my presentation. As we sort of said in the intro, I'm the commercial manager at Geodynamics. I am an accountant by trade, so I'm not an electrical engineer or a geologist or a geophysicist or any other fancy engineering name or term. So I will attempt to answer any technical questions you guys have, but I can't promise that I will be able to. I'll do as best I can. I wanted to give you a bit of an update. This doesn't seem. Here we go. Right, this first screen is really a notice, just basically a health warning saying I'm not trying to sell you anything, and some of our reserves in here are put together by Dr. Doon Wyborn, who is our chief scientist, and he's agreed to those numbers being in here. What I want to go over today is to talk about geothermal energy, geodynamics in particular, but geothermal energy in general, who Geodynamics are, some details on our main project in the Cooper Basin, and some of the parameters around that, what we've done in terms of work program to date, and what our objectives are over the next 18 to 24 months. Talk a bit more about the commercialization and how we're going to get this vast power source to market, and then open up to questions at the end. So an overview of Geodynamics. We are Australia's most advanced geothermal energy developer. We've been at this game for about 10 years. We've been listed for, I think, probably about 9 of those. We've raised significant capital over the period to date. Our main assets are driven by a major resource in the Cooper Basin. and that has both HSA and EGS types of geothermal, and I'll run through what each of those geothermal types are in a minute. But really, it's all for us at the moment. It's all about the Cooper Basin. This resource is huge. It's very large. It's widely recognised within the geothermal community that what we have in the Cooper Basin is a very special geothermal resource and not present anywhere else in the world. Certainly not in the extent and quality. We do have a joint venture partnership with Origin Energy. They own 30% of our Cooper Basin tenements, and we have our main focus at the moment is delivering power through a commercial scale demonstration plant, and that's where most of our focus is going, with the eye on a much larger prize of many thousands of megawatts into the coming decades, but at least 500 megawatts by 2020. And I'll talk about that commercialization program as we go through. We do have a strong management team with extensive geothermal field experience. A lot of that was built up in New Zealand, as I'll talk about in terms of the geothermal prospects in Australia. We are different to New Zealand, but New Zealand's been at this game for a lot longer than Australia. We do have some significant cornerstone investors, Origin Energy, Tata Power, who are a major Indian power producer, part of the Tata Group. We have Sun Super and a group called the Sentient Group, who are a venture capital fund based out of the Cayman Islands. These four cornerstones have a very diverse portfolio of interests individually, and collectively they all support us in our goal to commercialize this resource. We have obtained and continue to receive considerable significant federal government support, and under the Renewable Energy Demonstration Program, this REDP, we were successful in late 2009 in securing a $90 million grant under that program to deliver the commercial demonstration plant that I'll talk more about as we move through. Why are we looking at geothermal energy, and what are the prospects of geothermal energy in Australia? And really it comes down to the characteristics of geothermal energy being base load, being emission free, and being competitive with other technologies. You can see in this graph here that wasn't prepared by Geodynamics. It was prepared by a group called EPRI, who were commissioned by ABARE to investigate and look into the future and try and assess the future cost competitiveness of different technologies. Now the yellow blobs indicate where the emissions intensity, and the orange and grey bars indicate sort of cost ranges for these technologies into the future. And you can see the hot rocks geothermal and the hot sedimentary aquifer geothermal being very competitive with developing technologies and emerging technologies, and also having a benefit of zero CO2 emissions. You can compare along that graph with wind, which has zero emissions but slightly higher costs. And there are lots of bars in there for CCS technology, so carbon capture and storage technologies, that just like geothermal haven't yet been proven at a commercial scale and a commercially competitive scale. So the basic take from this slide is that if we can prove what we're trying to prove, we believe we can come down a cost curve and be competitive with a lot of other existing technologies, and more competitive with some of the future technologies as we move forward. In terms of the Cooper Basin project that Geodynamics is working on and have been working on for a period of time, you can see this map of Australia, Cooper Basin in that top right-hand corner of South Australia. We do also have some tenements in Queensland just over the border, and we do have some tenements in the Hunter Valley, and I'll touch on those in a small way later on. The Cooper Basin is where our main game is. There is a significant amount of granite underlying the Cooper Basin. It's high heat producing granite, and it is, as I said, extensive. Our resource potential in the Cooper Basin, we believe, if we can extract to the ability that we expect, to have a 6,500 megawatt electrical capacity dotted around the Cooper Basin in lots of small modules, producing power for 50 years. Now, that's an awful lot of power from a location that is a long way from anywhere, and I'll talk about how we plan to go through that transmission and linking process into the NEM as we go forward. But it's a significant resource, and that's why we've been focused in that area for such a long time. Our resources in Queensland and the Hunter Valley are much smaller. It's really about that the size and quality of that Cooper Basin resource, and I'll go on and explain why that quality is such. Now, in terms of the geothermal process, if you like, and the different methodologies of extracting heat and producing power in Australia, geothermal has been around in the rest of the world for many hundreds of years, and there's a significant amount of geothermal capacity in production, and there's probably in excess of 8,000. It's probably getting up to 10,000 megawatts of installed capacity now of geothermal centres around the world. Now, the vast majority of that is what we call volcanic geothermal, where the heat is coming from magmatic sources, volcanic sources, close to the Earth, and that's what's providing the heat to heat up water-filled aquifers. There's a significant amount of geothermal power production in New Zealand, in Iceland, in the US, and increasingly in Indonesia and that sort of ring of fire, the volcanic ring of fire around the Pacific region. In Australia, we aren't, or we don't have any volcanic activity, so our potential to use volcanic sources for geothermal power production are effectively zero in Australia. Now, that doesn't mean we don't have any geothermal resources, and that's what this picture is intended to show. Now, we have two models within Australia, and in the Cooper Basin we have both of these that we're trying to explore and exploit. Now, at the bottom of this cube, you see a hot fractured granite zone below about 4 kilometers. That granite is high heat producing granite. That heat is produced from the decay of radiogenic materials. Granites generally have levels of potassium, uranium, and thorium within them in their structures. Very low levels of those chemicals, but they are there nonetheless, and they do decay. Now, granites naturally produce heat, and as these materials decay, and if you go to a paddock or in a national park where you see granite outcropping and put your hand on it, it's not necessarily going to be hot, but it is producing heat. These granites down below 4 kilometers have been producing heat for many millions of years, and that heat is effectively stored and kept within the granite with this 4 kilometer blanket of sediment and rock above it. So we're targeting these granites because they've been there for a long time, and they've been blanketed and kept hot. Now, that granite's at about 250 to 300 degrees C, and in the Cooper Basin is very extensive, and therefore has a large capacity to produce significant volumes of electricity generation. Now, the concept with this, and it's really on the left-hand side of the cube, is that you drill a well into the granite, you extract fluid from the natural fractures which permeate through those granites. You extract fluid that's hot, you pass it through a heat exchanger on the surface to extract the heat from it. The fluid is then, once it's cooled, is put back into the reservoir. It goes back in, fills up or permeates through those through that naturally occurring fracture zone, and eventually heats up and sweeps the heat from the cool well to the hot well, and that process is a continuous closed loop process. So the fluid that's in the reservoir never actually gets vented to surface, which is different from other normal volcanic type geothermal processes that you may have seen or heard of around the world. Certainly sort of places like Iceland and New Zealand, they bring up the hot fluid, they use the heat and then just pump it into a river system, or they have done in the past. Environmental regulations are getting much stricter in those parts of the world and requiring them to put it back into the reservoir. So that's what we call EGS, or enhanced geothermal systems. On the right hand side of the cube is what we call sedimentary geothermal, or hot sedimentary aquifer type resource. Now there are throughout Australia, or throughout all parts of the world, there are porous sandstone reservoirs or layers that have water flowing through them. Now, in the Cooper Basin, that aquifer, or that porous sandstone layer, is heated by this hot granite 2 kilometers below it. So this layer is about 2,000 to 3,000 meters in depth, and the water through that sandstone flows quite readily. It is at a lower temperature, and we're looking at sort of 120 to 150 degrees C water within that aquifer, but it's much easier drilling. It's much easier to drill down to those depths. You can extract the heat in a very similar way. We use a slightly different process to extract the heat because it's a lower temperature, but that system is very similar. But it's water that's come from an aquifer. The heat gets extracted and gets put back into that aquifer. The characteristics are different in that, as I said, it is lower temperature, and because of that, the heat or the electricity generation production potential is lower in HSA concept than it is in the EGS concept in the Cooper Basin. So I've sort of sat on that slide for quite a while and tried to explain that. If there are any questions, please ask me at the end on the different methods. Now, in terms of what we've created, or why is this so good in the Cooper Basin, if you see the graph on the right hand side of this slide, we talk about production temperature versus the megawatts of energy you can produce from 100 kilograms per second of flow that you get from a well. So in our Habanero and Jolokia, sort of our Cooper Basin wells, which are targeting those granites at between 4 and 5 kilometers, we have temperatures in the range 250 to 300, which gives you between sort of 12 and 14 megawatts per 100 kilos a second flow. If you look at the HSA, it's a much lower temperature and you get much lower electrical energy for the same sort of flow rates. And you've got to weigh up the economics of these things, and given the flow rates and the depths we've got to drill to, at the moment we believe the EGS in the long term will be cheaper than HSA because of those temperature differentials and the energy differentials that you can get between an EGS and a HSA well. On the left-hand side, this picture here gives you a seismic array of a hydraulically stimulated fracture zone that we achieved within Habanero, which is Habanero is the name of a chile. It's the location of our main drilling site in the Cooper Basin. We drilled it in 2003 and hydraulically stimulated that reservoir. The different colors you can see on this graph are the stimulation activities that occurred at different dates. So the yellow yellow dots are events from the third stimulation, so we've done this 3 times. And the field, the fracture field, so the amount of enhancement in the reservoir that we created through the hydraulic stimulation process from one well in the middle was a 3 kilometre by 1.5 kilometre field, which is significantly greater than anywhere else that's been achieved in the world. There are geological reasons why the Cooper Basin is suited to this type of horizontal fracture stimulation, and that is to do with the stress regimes in the centre of Australia, and the fact that we're in the middle of a geographical plate and not towards the edges. So the stress regimes are such that we're ideally suited to create these pancakes of fractures that permeate out from a single well. If you ask me too many more technical questions on that, I'm not likely to be able to give you many more answers, because that's sort of the limit of my knowledge. Pretty much it. So what have we done to date in the Cooper Basin? We've drilled a number of wells at a number of different locations. We've been successful in achieving cornerstone support and cornerstone investment, government support and government investment, and Origin farmed into our investment in 2007, and we entered into another joint venture with them for this HSA concept earlier last year. We have purchased our own rigs. We've gone through and proved the concept in 2009, and we announced that early 2009, and I'll get on to what that means shortly. What we're aiming to do, so as I said, we've proved the concept. So what we've done is we've drilled down into the reservoir, we've hydraulically stimulated it, we've extracted heat through fluid from the reservoir, we've brought that fluid to surface, we've demonstrated that we can extract the heat from that, the heat energy from that, and then pass cooled fluid back down into the reservoir. And we've run that loop continuously for about 3 months. Now, that proves technically that you can extract some heat from the reservoir. What we haven't proved is that we can do this at a commercial scale for a commercial cost. Our goals over the next 3 years, ultimately we want to reach, within 3 years we want to reach final investment decision to build, commission and operate a commercial demonstration plant. We need to prove that we can stimulate and fracture not just at the Habanero location where we've stimulated one fracture zone, but in other at different depths within the Habanero reservoir, and also at other locations around the Cooper Basin. We need to complete a doublet at Habanero that demonstrates commercial production rates, so rates in the order of 2 or 3 times what we've created already through our initial testing. We need to demonstrate that to the market that we can actually produce electricity, and it's a fairly small step from extracting the heat to actually producing the power. We've got a power plant on the ground there ready to go. We've got a bit of work to do with drilling another well and getting a source of steam for that power plant, but we're working through that now, and that all of those things, so demonstrating that we can create reservoirs at will, if you like, demonstrating that we can create commercial steam flow, and that we can produce electricity, should be sufficient to allow to enable the market to invest further to raise sufficient funds to complete the commercial demonstration plant, at least to move forward with it. So what are we, in terms of trying to create commercial electricity production from EGS sources in the Cooper Basin, there are a myriad of technical risks. We're right at the cutting edge of technologies in terms of pressures, pressures, depths, chemical composition of the things we're drilling through and drilling to. What we've proved to date, and we haven't resolved all of them, and we are moving forward a systematic process to address those things. What we have resolved to date is that we have a tight reservoir down there at Habanero. We haven't encountered significant water losses. There's a great deal of pressure down there, so we haven't had the experience that other projects around the world that have been trying to do this have suffered from water losses out of the reservoir. We haven't had that. It's a tight reservoir that's saturated. We don't have to introduce water into the system. We've proved we've got the temperature there. At Habanero we measured temperatures of 255 degrees at about 4.3 kilometers. At Jolokia we drilled down a bit further to 4.9 kilometers and achieved temperatures in the order of 285, 290 at those depths. So we've proved we've got the temperature there. We've demonstrated at Habanero that we've got a reservoir there. We've stimulated that reservoir. We've enhanced it and made it bigger by drilling multiple wells into that and achieved hydraulic connection between wells. If you in the other and vice versa, so there is hydraulic connection within the reservoir. We've demonstrated that we're able to extract that geothermal heat, and we have done a lot of concept studies, thermodynamic modeling, transmission modeling, and hydraulic reservoir modeling too. So there's been a lot of work going on in the background with those things, as well as drilling and actually proving that we've got a reservoir and wells there. So as I said, the work over the next 12 months, 18 months is working towards getting commercial flows to be in a position to be able to then raise funds to produce a commercial demonstration plant, and we're aiming to produce or to build a 25 megawatt electrical plant in 2000 or by 2015. That will be supported by the $90 million federal government grant that I mentioned at the beginning of the presentation. But our tenements, we do have to demonstrate that we've got, or that we're able to achieve commercial flows, and that we can produce power from this. What we've been told time and time again isn't good enough for from a market sense. People want to see spinning turbines and light bulbs coming on and cooling the beer at Inaminka with our hot rock technology. So people want to see that power plant operating. So that's what we're aiming to achieve by the end of this year, early next year. In terms of the program to commercialization, we have got a number of steps to get us into this sort of 2020 position where we're producing 500 megawatts of commercial power plants. We intend to do that in a modular fashion, so drilling a set of wells, and the model at the moment is 9 wells to feed steam and power into a 50 megawatt module, and then we'll dot those modules around the tenement area, around the reservoir field, and end up producing 500 megawatts. That power will be collated and then sent down a transmission line into the grid. And I'll talk a bit more about the transmission line in a minute as well. But you can see the program there is to commission the 1 megawatt towards the end of this year, early next year, and run that plant for a period of time to give us confidence that we are actually producing steady, reliable power. We do have a good understanding of the reservoir and the chemistry of what we're dealing with, and we do have those commercial flow rates. We'll then be in a position to drill out further production wells and construct and build the first demonstration plant, and we aim to have that in place in early 2015. And by by running that plant for a period of time, nominally 12 months, we will then be in a position to roll out commercially and start constructing the first in a series of 50 megawatt modules, and at the same time start constructing transmission infrastructure to connect up those 50 megawatt modules and connect them into the grid. Now the construction period to start those 50 megawatt modules will take about 2 years, which is sort of around about the same time as it would take to construct the transmission line. If you started constructing it in say late 2015, early 2016, it would take 2 years to construct. Now that doesn't mean that there's obviously a lot of work which needs to go on beforehand to get us into that position, but that's the plan and the program. Anyone who's followed geodynamics or any geothermal player recently will know that there's or any renewable stock really recently will know that the market is pretty subdued and isn't particularly buoyant for renewable energy stocks for a number of reasons. The GFC and liquidity in the market sort of dried up because of the GFC, but also I think it's worth recognizing that there is pretty significant uncertainty and concern from investors and industry about the lack of a carbon price or sufficient carbon policies or climate policies that will encourage and drive investment in the sector. And that's causing great concern for us and for others. Now, this slide sort of goes to demonstrate a bit of that. Our current market value is around about 120 million. It fluctuates depending on the share price. Now, if you take our cash position and the value of our rigs, that's 120 million dollars. So we're basically being valued at net realizable assets with no value attributed at all to the 10 years of investment we've put in the development to date, and the resource value is effectively valued at zero. So a fairly significant undervaluation, we believe. Now, how do we increase that? Well, through the development timeline, there will be achievements along the way that will drive and push up that value, and operationally things like operating the 1 megawatt, completing or getting to final investment decision on the commercial demonstration plant, having that plant operational, taking the investment decision to expand commercially and connecting to the NEM will all have an impact in driving up that corporate value. We haven't seen it yet, but we hope that it does follow this path. Interestingly, I sort of see a corollary with the coal seam methane industry or the shale gas industry in Australia and the US, in that for many years there were a number of small explorers who were trying to crack this coal seam methane nut. How do we dewater? How do we do this at a commercial scale for commercial cost? And we got to the point where a number of them did, and the value of those resources went through the roof overnight. And there's been a significant volume of, or a significant amount of value attributed to those coal seam methane assets and the LNG potential of those before the LNG investments have actually been made as well. So a significant value uplift in those assets, and there's still a significant multi-billion dollar investment to be made before they're actually commercialised and LNG trains are operating off the coast of Queensland. In terms of other exploration, as I said, we are looking at hot sedimentary aquifer opportunities in the Cooper Basin, as well as our deep granites, and our first wells we've got on here late 2010, but there was a fair amount of rain and flooding in the Cooper Basin over the last few months, and that's pushed that out. We hope to spud the first well to target that aquifer in the very near future. But they are much lower temperatures. We're looking at sort of between 130 150 and a total geothermal potential of around about 300 megawatts if we can make it commercial in that area, compared to the sort of deep granite resources of 6,000. We do have tenements in Hunter Valley in New South Wales, and we are preparing to drill a well there, but again, that's lower temperatures, much smaller resource. We do have some government funding support to do that, but it's a very different concept, and well, similar concept but a very different prospect than the Cooper Basin, which is much larger. Queensland is still in the very early stages of exploration. We're going to undertake some shallow drilling this year to further delineate some of the prospect there and to determine further future work in that area. Question that's often levelled at Geodynamics and others in the Cooper Basin region is, how are you going to get this power out? Yes, great, you can produce 6,000 megawatts of power. There's no grid. How are you going to get it out? Well, the first tranche of power that we produce, there are a number of options open to us. We can use the power ourselves. Our camps and facilities in the Cooper Basin are currently run on diesel. Our rigs are currently run on diesel. So there's certainly an opportunity there to replace that diesel and use our own emission-free baseload power to power the rigs and the camp. There are existing local customers, or fairly local customers, at Moomba and Bellera, gas processing plants. Currently they use gas-powered compression and gas engines for their electricity generation. As the price of gas increases with LNG terminals coming online, that gas gets increasingly more valuable. Instead of using it yourself, you can sell it. So there's potential there to supply those processing centres with power. And we're also looking at new local consumers. How do we get people into the area? What sort of industries can we get into the area? And is in things like data centers, very heavy energy users, very cheap transportation of their produced power. I mean, it's much cheaper to transport gigabytes than it is to transport megawatts on transmission lines. Obviously, requires some infrastructure and some design work. Challenges with working in the desert, but certainly an opportunity that we're looking at. Ultimately, though, we need large-scale transmission from the Cooper Basin into the existing grid to start replacing, supplanting, coping with load growth, natural load growth from the baseload geothermal power in the Cooper Basin. Some of that we're linking in with this the CENI or CENI process that the AEMC are driving, and we're certainly heavily involved in that. We see the ability to leverage significant resources in the Cooper Basin, not just geothermal but solar and gas. There are vast tracts of land out there that could quite easily be solar thermal fields. The thing that they're lacking at the moment is transmission infrastructure. If we can sort of combine and link resources, there's no reason why we can't build the transmission infrastructure out there. It is expensive. There's no doubt about that. But we believe we can produce EGS power and deliver EGS power from the Cooper Basin for around about $100 a megawatt hour in the future. That will be, from a cost perspective, about $85 long-run marginal cost of power production, at about $15 a megawatt hour for the transmission cost, for the transmission element. So it is significant, but it's not insurmountable compared to the price of $100 a megawatt hour delivered baseload emission-free power. So a few facts on transmission. We had Wally Parsons do a study for us. I won't go into it in too much detail, but basically it takes 5 years to develop, half the time in planning, half the time in construction. So we need to start getting some planning work in place, not immediately, but in the next 12, 18 months to enable us to meet that development time, to link that development timeline. One of the things that we're cognizant of with this CINI process is transmission has a long lead time. Anything to do with regulated transmission is very bureaucratic. If we undertake any planning, we want to do it once, we want to do it well, and we want to avoid any duplication. We don't want to go through the process of planning a transmission line and then having a CINI process running beside it or tagging onto the end of it and it being the work that we are doing not being able to be used. So we want to make that planning flexible, and we want to start it early. So we are heavily involved, as I said, with that CINI process and trying to link into whatever mechanism comes in place. At the end of the day, if it doesn't come in with the CINI process at the start, we will be raising funds to build a transmission line in conjunction with raising funds to commercialise the power plants out there. And to be honest, raising funds for a transmission line are much easier than raising funds for commercialising the geothermal power plants anyway. I mean, it's a very proven, easy technology to work with. Finally, I'd just like to thank our joint venture partner Origin. We wouldn't be able to do what we do in the Cooper Basin or progress our exploration without them. So we acknowledge their support and their efforts. And our vision is that we will become a world-leading Australian geothermal energy company supplying competitive zero-carbon energy and baseload power. And that's a lovely picture of our rig at sunset in the Cooper Basin. So more than happy to ask or to answer some questions if there are any available.
Thank you, Alistair. That was a great presentation. I've just had a few questions come through. The first one is, why hasn't anyone explored this sort of process before?
They have, and as I said, the traditional volcanic geothermal has been around for many hundreds of years. This EGS type concept of targeting granites and trying to exploit those granites first really came about in the States in the 60s. In that oil shock in the 60s, there was a lot of funds put into that. When the oil price died down again, the interest and funds sort of dried up for those projects. And that's a similar story to Cornwall in the UK. There was a lot of EGS exploration that went on in Cornwall back in the 60s and 70s. Geothermal power or EGS power will be more expensive than fossil fuel plants in the absence of a carbon price. There's no doubt about that. Delivering power at $100 a megawatt hour, we can't compete with a traditional coal-fired power plant. I used to work at Araring Energy, and long-run marginal cost of $30 or $40. There's no way we can compete with that in and of itself without a carbon price. So it requires policy settings or people to get scared enough about energy security for people to start investing and investigating new energy sources. I hope that answers the question sufficiently.
Thank you. We've had another question. Are there any other countries currently involved in this technology or looking into developing this further?
Yes, there are. Other EGS projects around the world currently being explored and developed. I mean, you're looking at Japan, the US, Europe, France, Germany, Turkey. I think there are projects in Hungary. There's a few Eastern Bloc countries where they're looking at exploring new geothermal resources. The UK, and there are a plethora of other countries that are trying to exploit traditional volcanic type resources as well. Indonesia is just going through a huge expansion program. Chile, those South American countries trying to ensure their energy security issues by exploring for new technologies. Australia's in a unique situation that it doesn't have the energy security issues that other countries face, so the drivers there aren't as great. But certainly there's an interest in developing renewable, clean technologies at the moment, and so that's growing in the public populace. It might not be growing in, or it might not be sort of eventuating in government policy, but I think it will eventually.
Thank you. We've had another question from Brendan, and he asks, what's the type of pipe and the size which will be used to transmit the steam to the surface, and also the expected life of the pipe?
Yeah, I can't give you sort of technical specifications, but in terms of the material specifications, but at the moment our production wells are cased down to the granite with 8.5-inch casing, so there's sort of 4,300 meters of casing that's cemented in place, and that's our intended production size for getting the fluid out of the ground.
Okay, thank you. And finally, how many sites are you aiming to develop?
Well, as I said, if we're thinking of 50 megawatt modules, and there are 6,500 megawatts of capacity out there in the Cooper Basin, I mean, we'll need to develop many dozens of sites where we'll drill multiple wells, and the process really is you drill the wells and prove up the resource, and then you connect the pipes on the surface and through a heat exchanger then build a power plant on surface. So there'll be, as the rate of expansion will be driven by a lot of things, but and a lot of elements will go into that, but we would and should have multiple rigs operating and multiple sites being developed continually through decades, I suppose, as we commercialize the resource. And that's obviously just in the Cooper Basin. There may well be other geothermal prospects that are drilled and commercialized around the country.
Okay, thank you, Alistair. We have a few more questions that have come through, but we might just leave it there and wrap it up.
Okay, if people want to send through questions to you guys, I'm more than happy to answer them electronically in an email or something, and post the answers up.
Thank you.